improper integrals are going to be situations where, so like when we've talked about integrals in the past, there's been two kind of rules that we kind of just ignored, right? They were like there, but we didn't really pay attention to them because they didn't really matter to us unless they gave us a problem that involved it, and they just don't usually do that, right? Up until this point, okay? So two of those things were, one, when you had a definite integral, the function inside had to be continuous in order for you to evaluate the definite integral with the fundamental theorem of calculus. Because like if it jumps up, right, or has like a big vertical asymptote in the middle, like you can't just find the area under that curve by the normal rules, okay? So we're going to address that today. And then the other rule was that the limits themselves had to be nice numbers. They were not allowed to be infinity. I'm sorry. I'm trying to get the desk fixed. It's the worst. Catches you off guard too. The limits had to be finite numbers in our past. Got it. So today we're going to talk about, okay, so what if they were infinity? Or what is their, Lexi, you are at this table now. What if the limits are infinite? Or what if there is an infinite discontinuity specifically somewhere in between? Okay, so like if you have a vertical asymptote at some point in that interval, or what if your limits are infinity or negative infinity, okay? These are called improper integrals, when there's either an infinite discontinuity somewhere between the endpoints or at the endpoints, or when there's a limit of positive or negative infinity, okay, like at the top or the bottom. So how in the world can we even talk about such a thing? It's actually a little bit intuitive. So let's look at an example here, okay? So this right here is what we would define as an improper integral because there's an infinity in the limit, okay? So if we look at the graph of 1 over x squared, just kind of like this section of it, if we start at 1 and go to infinity, remember an integral is the area under that curve, right? So if we ask ourselves, what's the area under this curve from 1 to infinity? Technically, that's an infinite area, right? Like this is going to keep going and going and going and going and going, and it never touches. So that area is an unbounded region, right? It doesn't stop. But in calculus, what we're going to say is, okay, but it's getting so small. Is it approaching a particular value? Like, is it getting really close to a number of areas since it's getting so small then at the end? And that's exactly what we're going to be talking about here. And in this case, yes. And it's going to approach the value of 1. Okay, so that area is going to get closer and closer to 1 as that goes to infinity. Okay, and that's what we do with improper integrals. So so what we're going to do is we're going to look at limits, right? So we're going to replace like whatever bound is infinite with a letter like b. We'll find the antiderivative like we usually do. We'll plug in the bounds 1 and b and find that answer. So in this case, that would be 1 minus 1 over b. Then we'll ask ourselves, okay, what happens as b goes to infinity then, right? What happens as that limit goes to infinity? And if we take the limit as b goes to infinity of this antiderivative with 1 and b plugged in, what happens to this fraction right here as b goes to infinity? It goes to 0, right? So this is just going to be equal to 1. So that area underneath will approach 1. So we say it converges to 1. So an improper integral will either converge or diverge. And if it converges, then that's what the area is approaching. Does that kind of make sense? Kind of weird. We're going to be integrating and doing limits. So we're bringing back limits. That's honestly, I think, the hardest part. So here's the official definition of improper integrals with infinite limits. So infinity or negative infinity in the limit. To determine if they, this is the one thing that's kind of important about this section is if you watch videos on this, people are very lax with using correct notation, and it is important on free response questions to use correct notation with this. So just kind of pay attention to that if you like go watch videos as they kind of do it. I'll kind of point out a few things that you might see that you kind of need to be careful to avoid. Okay, lots of people take shortcuts with the notation. So this is kind of what we would want to do. If we have an infinite limit, like in the top, we would replace that with a letter. It doesn't really matter. And then we would just take the limit as b, whatever that letter is, approaches infinity. And we would treat this like we usually would. Okay? If we have a limit in the bottom like negative infinity, just replace it with a letter. Take that limit as a approaches negative infinity. If we have both top and bottom, we have to do both limits, separate it. You can kind of separate it wherever you want. I like 0. 0 is a great way to separate it. And now we have 2 improper integrals, and we will do the same thing with each one of those. So if in either of these cases the limit exists, then the improper integral converges. If the limit does not exist, then it diverges. Okay? So let's actually do some examples. So the very first thing we're going to do is we're going to replace the this is an improper integral because there's an infinity in the top limit. So we're going to replace that infinity with a b, or whatever letter you want. And we're going to do the limit as that b approaches infinity. Now we're going to treat this problem like we usually would. Find the antiderivative of dx over x. That's ln of x. So we're going to write the limit out in front. So the antiderivative of dx over x is ln of x. And then we're going to evaluate that from 1 to b, just like we would for any definite integral, right? If you had number limits, that b is just like a placeholder for a number. And then if you remember, just don't forget, we're going to write down our limit out in front. We're going to plug in b, subtract, plug in 1. What's ln of 1? 0. Yeah, 0. And then it's helpful maybe to even think about what the graph of ln looks like. The limit as b approaches infinity of ln, what happens to a natural logarithm as x approaches infinity? It gets bigger and bigger and bigger, right? So this is going to go to infinity. So this limit equals infinity. So does this limit exist? No. If it equals infinity, it doesn't exist, right? It's not approaching a number. So what would we say about this improper integral? It diverges. Yep, it diverges. So the area bounded between 1 and infinity under ln, or under 1 over x, is not getting small enough over that as we go to infinity to approach a particular value. Sometimes it can be helpful to kind of like look at the pictures of this if you want to graph them and kind of look at what that area looks like. Yeah.
So all we say is that we have to say without.
Yeah, a lot of times these questions will just be multiple choice convergent, divergent, or if it converges, what does it converge to? That's it. If it's free response, that's when we have to be a little bit careful that we're writing the notation down correctly. All right, so this one diverged. Let's look at one that converges. So this is an improper integral because there's an infinity in the top limit. So we're going to replace that limit with a letter. Take the limit. I'm going to use b again. B approaches infinity. Treat this just like we would any other definite integral now. So we're going to find the antiderivative of e to the negative x. Just put our limit out in front. Antiderivative of e to the negative x is negative e to the negative x. You got to deal with undoing the chain rule because of that negative up there. And then we're going to evaluate it from 1 to b. Write down our limit. plug in b, plug in 1, subtract, so it'll be plus e to the negative 1. When you're doing limits, especially as we go to infinity, and you have negative exponents, a good rule of thumb is just rewrite the negative exponents as positive. It's really hard to find limits as we go to infinity with negative exponents. It can kind of hurt the brain. So we're going to rewrite these as negative 1 over e to the b plus 1 over e. E is an exponential function, right? So as x gets bigger and bigger, e is going to get bigger and bigger and bigger, right? So if b goes to infinity, e to the b is going to go to infinity. So what's going to happen to this fraction? Smaller and smaller and smaller and go to 0. So this is going to be 0 plus 1 over e. Like I said, the hardest part I think about this section is going back, bringing limits back to the brain. So does this limit exist? Yeah. So we would say this converges to 1 over e. So the area of this unbounded region is approaching 1 over e. So if you go watch a lot of videos or maybe like see someone else do this, the poor notation that people will use that the AP test does kind of care about is a lot of people will not put this limit here at all. They'll just leave the infinity up here, and then like here they'll put infinity here where the b is, and then they'll just plug it in, right? But they want you to acknowledge that infinity is not a number that you can just plug in, right? It's in order to quote plug it in, we need to talk about limits, right? So that's you need to include the limits. If you see people doing that shorthand notation, just don't get caught up in it. Okay. Any questions about those two so far? All right, you're gonna hate me for this one, but I'll help you through it. This is an improper integral because there's an infinity in the top. So let's start by replacing that with a letter. The limit as b approaches infinity. Find the antiderivative of the function inside. What's the antiderivative of 1 over x squared plus 1? Yeah, arctangent. I know. I'm cruel. No, this is like the one that they tend to like to use. And after we do it a couple times, you'll be fine with it. They don't tend to use a lot of them, but arctangent is the one that they like to use. Now, something you would be fine doing is skipping this step right here. Like if you jump straight from here to here, that's totally fine. Like you don't have to do this part as long as you put the b, the limit, and the b here instead. Okay, so we're going to plug in b. Plug in 0 and subtract. I know. What the heck is arctangent of 0? Or how do we find the limit of arctangent? Well, this is the one graph they like you to kind of use. So I don't expect you to remember this off the top of your head what arctangent looks like, but that's why we're going to talk about it right now, okay? But do you remember that tangent kind of looks like this, right? And those asymptotes are at negative pi over 2 and pi over 2, right? So arctangent is just the flip of that in y equals x. So you've got now asymptotes horizontally at pi over 2 and negative pi over 2. And it goes like this right through the origin. So maybe you remembered that's what that looked like. But I probably would not have remembered that's what that looked like. So what is arctangent of 0? 0. And as b approaches infinity, what happens as x approaches infinity for arctangent? It approaches pi over 2. So this is going to be pi over 2 minus 0. So this converges to pi over 2. Not so bad so far, with the exception of arctangent being thrown in there. So let's do a more fun one. Fun might be a strong word. This is the part of calculus I personally don't really enjoy. So, sorry if I ever seem negative. But you got to go through it to get to calculus 3, which is so much fun. So hopefully some of you will take calculus 3 in college. That's when you get to do your triple integrals. It is so much fun. It's really cool. It's like, wow, I can see how calculus could be used in real life, like a lot of times. Okay. So, for this guy here, we have an improper integral because of the top limit. So let's replace that with the letter. We have to find the antiderivative of this thing. You could distribute, but you're still going to have x times e to the negative x. So we're just going to kind of like leave it as it is for now. For x times e to the negative x, or for 1 minus x times e to the negative x. Any ideas what we might have to use? Yeah, it's a product, right? And it's not like a nice u sub, so we're going to do some integration by parts practice. However, integration by parts takes some steps, right? So personally, I would not recommend doing it right here, right? Don't worry about the limits and the ones and the b's. Like, let's just pause. Let's come over here, and let's just find the antiderivative of 1 minus x, e to the negative x, and then we'll go back and plug it in. There's just too many things to keep track of, in my personal opinion, if you have to deal with the limits and the ones and the b's, while also doing multiple steps. Should e to the negative x be my u? No, right? It's exponential. That always should be the very last choice. So 1 minus x should be my u, and dv should be e to the negative x. du is going to be negative 1. V is going to be negative e to the negative x because we're doing an antiderivative. And remember, with that negative up top, we have to undo the chain rule. So you can do a u sub if you want, or you can just think about the fact that if I did the derivative of that, I would get a negative. So I have to combat that negative there. So we'll have u times v. So negative e to the negative x times 1 minus x minus v times du. So that's going to be positive e to the negative x. And then the antiderivative of e to the negative x is negative e to the negative x. So we're going to end up with minus negative e to the negative x plus c plus e to the negative x. We don't really have to worry about the plus c because we're going to go put that in a definite integral. And remember, with definite integrals, we don't need the plus c on the end. This is why I personally would not have done all of this step while also putting a limit and some b's and 1's in there. I would just do this separately and then come back. You could if you want. For the sake of this, I'm going to leave it like this for now.
So we don't regard the question.
You don't have to because we're going to go plug it in a definite integral, right? And when we're doing definite integrals, we don't need it. So, okay, so now let's go plug this in. So the limit as b approaches infinity of this antiderivative, negative e to the negative x, 1 minus x plus e to the negative x, evaluated from 1 to b. That's why we get to disregard the c. It's because we're doing a definite integral. So we'll plug in b. I am also going to rewrite my negative exponents as positive at the same time. So I moved the e to the negative b to the bottom. Yep, thank you. So I'm plugging in b. I'm moving this to the denominator to make it positive, and I'm moving this to the denominator to make the negative exponents positive. Because whenever we're doing limits as infinity, you really want to do that. And why don't we distribute this negative up here as well? Ah, yes. Did that earlier too, both times. Sorry, I forgot to plug in 1 for that other x over there. So let's go ahead and distribute that negative. And then I had an x here. I forgot to plug in 1. So if we look at our limits, this limit right here, not bad. E as b approaches infinity is going to go to infinity, so that'll go to 0, right? This guy, though, we're going to have infinity in the numerator and infinity in the denominator, okay? Technically, you would be allowed to look at that and be like, well, isn't the exponential function in the denominator going to grow faster than the linear function in the numerator and go to 0? Yes, that's allowed, but we're going to practice using L'Hopital's rule, okay? So infinity over infinity means we could use L'Hopital's rule, right? So L'Hopital's rule says take the derivative of the top. Derivative of negative 1 is 0. B is 1. Derivative of e to the b is e to the b. And then we'll do the limit as b approaches infinity of the other 1 over e to the b. This will be 0 because we'll have 1 minus 1 is 0 divided by e to the 1 plus 1 over e to the 1. And now if we were unsure before that original limit also goes to 0 because the exponential function in the bottom grows faster, now we definitely know that this is going to go to 0 because e is going to keep getting bigger and bigger and bigger. So 0 plus 0 minus 0 minus 1 over e is equal to negative 1 over e. Told you this one was going to be fun. Converges to negative 1 over e. Yeah. Yeah. I'm just kind of trying to make sure nobody gets lost where everything just disappeared to.
Can you explain how you use the
Yes. So this right now, if you think about what's happening, this is going to go to infinity, right? If b is going to infinity. And this is also going to go to infinity if b is going to infinity. So we have infinity over infinity, right? So we can use L'Hopital's rule. If b was an x, let's just, for the sake of our brains, think about b being an x. You would do the derivative of -1 plus x. What's the derivative of -1 plus x? And then if b was an x here, what's the derivative of e to the x? E to the x, right? So we just do, L'Hopital's rule is just derivative top over derivative bottom, and then you do your limit. Any other questions about this one? Because I know there was a lot. Okay. We're going to do one more really fun one. This one is a pretty tedious. So if you feel confused or lost, don't be afraid to go back and watch the video later. I know that there's a lot, but I just kind of want you to see a general situation. And unfortunately, these usually are not very easy situations. Why are you not moving? What's up? What do you mean by all of them? Yes. You mean this and this? Not this. Oh. Because this did not have the form infinity over infinity, right? That's why we just did the limit of this right here. We're doing the limit of this and the limit of this. So I broke it up into two limits. Sorry, yeah. Good. So if we're doing the limit of the whole thing, so we first do the limit of this one. That's where we had to use L'Hopital's rule because it was infinity. Then I broke it up into the limit of this one right here. Does that make sense? So this went here and this went here. All right, buckle your seatbelts for this one. I know. And you two especially are going to be like, what the heck? Okay, this has limits in the top and the bottom and that are both infinity to a negative infinity. So we need to break it up into two improper integrals. You can start at whatever number you want. I like 0, so let's do 0. Okay, so we're going to break this up. We'll do the limit as a approaches negative infinity. We'll replace the bottom limit with a. We're going to break it up into 0. And then 0 to infinity. But we're going to, I'm also replacing them with letters at the same time. So I'm kind of doing 2 steps in one here. I'm breaking it up into 2 integrals and doing the good calculus student work by replacing the infinite limits with letters. And I picked 0. You could pick whatever number you wanted, but I like 0. This is an arctangent antiderivative where u is e to the x, a is 1, because du is e to the x dx. So because this is e to the x over 1 plus e to the x squared. That's what e to the 2x is. So that is du over 1 plus u squared. So these are going to be the limit as a approaches negative infinity. So the antiderivative will be arctangent of e to the x, since u is e to the x, and a is just 1, so that's it. Evaluated at a and 0, plus the limit as b approaches infinity of arctangent e to the x. Hey, Allie, your new seat's right there. From 0 to b. Welcome to the chaos. Yes, I am recording it right now. Yeah. Okay, So now we're going to plug in our values here. So we're going to plug in 0. Plug in A and subtract. Plug in B. Plug in 0. Subtract. E to the 0 is just 1, so this will be arctangent of 1. That's just a constant. So the limit of a constant will just be another constant. So that will be arctangent of 1. As A approaches negative infinity of e to the A, that's actually going to go to 0 because this is e to the x, right? So as x approaches negative infinity, e goes to 0. So this is going to be arctangent of 0. But as b goes to positive infinity, e will go to infinity. So this will be arctangent of infinity. Minus arctangent of 1. We talked about what arctangent of 0 was earlier. That was 0. We talked about what arctangent as we approach infinity is, right? That was pi over 2. Arctangent of 1 is not a nice number. And because I told you you could pick any number you wanted, we could have plugged in like e to the 5 here if we wanted, right? So it didn't, but does that really matter that we don't know what arctangent of 1 is? No, because we got arctangent of 1 minus arctangent of 1, which is going to be what? 0. So those just go away. That'll be 0. So this is just going to be equal to pi over 2. So this insane nonsense converges to pi over 2. I'm glad you find it nice. Yeah, the goal is nice. How we got there, I don't know whether any of you find this enjoyable, but this is my least favorite. We're beginning my least favorite part of calculus. Okay. So the last couple examples we're going to do are not when they're improper integrals because of infinite limits, but because you have an infinite discontinuity somewhere in the interval, okay? So sometimes the infinite discontinuity might be at the endpoints of the intervals. Like, so when I say infinite discontinuity, I mean a vertical asymptote, okay? Sometimes the infinite discontinuity might be somewhere in between the interval, okay? Why is this an improper integral? Well, let's pretend we have a function here that has a vertical asymptote right here at 4, and we're looking at the integral from 1 to 4. This may not seem like an improper integral because you're looking at 1 and 4, right? But if we look at the area between 1 and 4, that doesn't stop, right? That's going to keep going. So that's why this is an improper integral, okay? So a lot of times they'll be at the endpoints, and in that case, we're going to turn it into a limit. I think these limits are easier to understand with actual numbers. There's too many letters here, so we'll kind of explore this definition with the actual problem. If the infinite discontinuity is somewhere in the middle of the interval, you have to break it up. Like if it's at C, you have to break it up from A to C and C to B into two improper integrals. Anytime you have to break it up into two improper integrals, if one of them diverges, you're done. It diverges. It can't converge if the one of them diverges and one does not. Does that make sense? Okay. So let's look at this one. So this first one, why is this an improper integral? The zero in the bottom limit. If you look at this original function and you plug in 0, what are we going to get? Does not exist, right? There's going to be a 1 divided by 0, right? Which we know that means vertical asymptote when you have a number divided by 0, right? So there is an infinite discontinuity at x equals 0. There is a vertical asymptote there. So that's why this is an improper integral. So just like we did before, we're going to replace that improper part with a letter. I'll use A for the bottom limit. So we're going to place that 0 with A. And now we're going to do the limit as A approaches 0 from the right. And this will be of x to the negative 1/3 dx. So why did we approach A? Well, A approaching 0 makes sense, but why did we do it from the right? Well, because we're looking at vertical asymptote at the ends, right? Do I care in between 0 and 1? Do I care what it's approaching from the left of A? No, that has nothing to do with this improper integral. I only care about the right. So if you were looking at the top limit, you would approach from the left, okay? So now we do what we usually do with definite integrals. We find the antiderivative. Don't forget to write down your limit. We're going to add 1, so we'll get x to the 2/3 times 3/2, and then evaluate from A to 1. Plug in 1. Plug in A and subtract. Three halves times 1 to the 2/3 will just be 1. That's a constant. So the limit of a constant, or not 1, 3/2, sorry. Limit of a constant is just a constant. And the nice thing about when we do limits is we approach numbers. Remember, they always just try to plug it in first, right? That's always what we try with limits. So we're just going to plug in A equals 0, which is just 0. So this is going to be equal to 3/2. So it converges to 3/2. So even though there's a vertical asymptote at the end point, this area gets smaller and smaller and smaller, and it gets close. I mean, this is the exact same function, but like the idea, that area still approaches 3/2. So let's do another one. Why is this one an improper integral? 0. Yeah, that's going to be another infinite discontinuity, because if you plug 0 into the original function, it'll be 1/0, vertical asymptote at 1/0. So infinite discontinuity at x equals 0. These are the ones where you really have to be careful, because a lot of times if you do this problem like normal and you plug in, like, there can definitely be times, especially if the infinite discontinuity is in the middle of the interval, if you just plug in the top and bottom limits like you usually do and evaluate, you might totally get a different answer if you didn't realize there was an infinite discontinuity in the middle. So these are where kind of like it's easier to forget that it is an improper integral because they're numbers. So we want the antiderivative of x to the negative. So we're going to do the limit as A approaches 0 from the right. Replace the 0 with an A. Since it's the bottom limit, we're looking from the right. Antiderivative of x to the negative 1/3 will be x to the negative 2
divided by -2 or times -1/2. Don't forget your limit. Evaluated from a to 2. Plug in 2. And we'll have -1 over 2 times 2 squared. Subtract. Plug in a. That constant will be -1 over 8. Try to evaluate our limit by plugging in 0. Sorry, I had too many negatives here. When I plug in 0 here, I'm going to have 1 over 0, right? So does that exist? No, there's a vertical asymptote there. I'm approaching 0 from the right, so technically this limit does equal either positive or negative infinity. Now, do we already know this diverges? Yeah, right? Because the limit does not exist, right? Now, let's make sure we know what the actual answer for the limit is correctly. So here, if this is 1 over 0, this is positive, right? And we're approaching 0 from positive numbers, so it's just going to be positive infinity. So this diverges, but this limit technically, if we were asked to write the value of the limit, would be infinity.
The teachers, pardon the interruption. Students, as we embark on the second semester, we want to make sure y'all are all aware of the attendance requirements as they relate to exam exemptions. We know semester exams are not until the end of the year, but your attendance is one of the contributing factors to whether you will or will not be exempt. It is imperative that you understand that you can have no more than 3 absences. That includes unexcused absences, excused absences, and even health absences such as dentist appointments or doctor's appointments in any course to even be eligible to be exempt from your exams. Other requirements include grades, but your attendance is what you need to be aware of first. So again, you can have no more than 3 absences in any course to be considered eligible for an exemption. Thank you.
Because then that'd be really unfair.
Yes, no, that would not be fair. Okay, for this very last one, we're going to kind of go through it briefly because it's very similar to the one we just did. But why is this an improper integral? Because even though -1 and 2 are not infinite discontinuities, 0 is. And it's in the middle, right? So we would have to break it up into 2. Now, if this was a multiple choice question, you could be done right now because this is the exact same problem we just did on the last one, right? And what did we find out about this one? It diverged, right? And so if that one diverges, the whole thing diverges, right? But just for the sake of kind of learning, so we already know this is going to be plus infinity. We just found that one was infinity from the last question. But let's do this one for the sake of learning. If all you were doing was telling if it converged or diverged, we would be done. But if we needed to find the limit, we would replace the 0 with a b. We do the limit as b approaches 0 from the left. Antiderivative is -1 over 2x squared, just like we saw in the last problem. plug in b. Plug in -1. And this guy over here is also going to be an infinite limit because if you plug in 0, you're going to get -1/0. So we definitely know there's a vertical asymptote. As far as kind of remembering appropriate limits here, we're approaching 0 from the left. So we're going to be plugging in negative numbers, right? If we're in 0 from the left, but then we're squaring them. So those will become positive, and then we have a negative whole number. So that would technically be -infinity. Because remember, you just kind of see what numbers you're plugging in to decide if it's positive or negative infinity. We just know it's going to be one or the other because it's a number divided by 0. Okay? So that is the wonderful, awful world of improper integrals. Yes. What'd you say? Oh, I don't know. 1/2. I don't know where the 0 came from. Sorry.